duplication, like x, you don't want to create an axis called x plus y, because that's duplicating, because this x plus y can be reduced into x and y axis, right? So you want the most primitive set of basis function that you can build on primary vectors, and you think in vector space. So in the same way, you can think of these orthogonality of basis function in this way, is that you can build non-duplicate. So these are the most primitive basis function. You cannot express one of the basis function in terms of the other. You cannot write a linear combination of, let's say, this guy in terms of the other, and that is a basis function. Okay. So you once you use have this kind of definition, what you get is that you get a couple of terms coming out. So these are value. These alpha and beta are just integration value after you do this math. You got some numbers out, and what you have is that in fact, if you calculate this for two orbital case, right? So two orbital case, your energy is just depending on alpha, which is one of the integration for your basis set, 2 times beta, which is another integral values, right? And cosine function depending on k, right? So what you got is something like this, right? So depending on the sign, I tried to explain last time that depending on the sign of alpha and beta, and alpha and beta depends on the interaction between the basis functions. You could have a lowering of value. So if you have alpha is my average value, and if beta turn out to be negative, more stable, right? If it's more stable, you in fact as this lowering down here. But if beta is at another k point, you can see how it changes when cosine Ka, it will change sign, right? And when you change from one angle to another, it's going to oscillate, so you're going to move up here. So you would have low value here and high value due to this cosine function. Okay. And then if you are talking about another state, it will occur in a different way. You will have alpha, beta will be positive. So when you're talking about k equals 0, it will actually higher than alpha, and then when you go to another k point, it becomes lower. And so, but the key point is that you would have this gap, and this gap again corresponds to the band gap that we'll see. We have seen from solid-state physics that we just talked about, and you can get exactly the same thing using this linear combination of atomic orbital approach to understand the origin of these vectors. Okay, and we have tried last night before we go on was talking a little bit about these. It's good to have some picture to think about these this diagram that I just shown here. This corresponds in effect to if you look at this top point, a linear combination, your atomic orbital. So in the bottom curve, it corresponds to combination of s orbitals, right, at different points on your chain. This is my linear chain of my state, right? This is a one-dimensional periodic chain of atoms, and each atom has an s orbital, and I can combine these chain of s orbital in different ways. So if you combine it in a constructive way, they have the same sign, and I put it positive here. Then you will get this the bottom here. But if you combine it in alternating sign, changing sign, then you would have this point here. Okay, so that's what happens when you combine s orbital, and you can combine p orbital as well. So here, if you combine p orbital in a bonding arrangement, you get this point. And if you combine anti-bonding sigma star type arrangement, you get this point over here. And And this is how you generate these kind of curve. And the gap between these two, of course, correspond to conduction valence band, and conduction band. If you extrapolate further like this, okay. So I think we can understand from both perspectives, both the physics perspective and the chemistry perspective, how the origin of band gap work and the entire band structure that you see. So this is our basis. And later on today, I hope to talk to you a little bit about what happened at the surface. And here we're talking about one dimension, and then you can extrapolate to 3 dimension, right? So in 3 dimension, for the bulk case, any material, so you will see all these rather complicated looking band structure that you see. Okay. So here I say the Brock function is written as, remember what the Brock function is basically a periodic function times a exponential, right? This is a plane wave kind of thing, e to the minus kx, or k times r. You can extrapolate into, if you have an exponential with an imaginary number, is the same as cosine theta plus I sine theta. You can always expand your exponential this way. And so this key point is that this u of x is my periodic function corresponding my linear arrangement of my atoms in my lattice, right? And the requirement for this to show that it's periodic is to ensure that this function is the same, is identical if you shift this position by the periodicity, and this periodicity is A, right? So if you shift from one atom to another, you should not see any difference. The function, this periodic function, should be exactly the same. So that's the requirement about this periodic function, and A is the lattice spacing that you have here. And you can define it this way. The k here, the wave vector, is simply 2 pi divided by lambda, and n here is we can think of it as a quantum number, and big N here is the number of atoms. So you can generate your wavelength in this way, you know. And so if you look at it this way from the Brock function perspective, you can have essentially you have a periodic function here, u of x like this. And then you have this 2 sinusoidal waves, right? One corresponds to real space, the other corresponds to imaginary space. So one is the dash curve, the other is solid curve. You multiply this together, right? If you consider just one of them, you would get these. If you multiply, let's say, this function with this function, you get this funny-looking arrangement. Okay, so that corresponds to one periodicity k value, right? If you change this periodicity of the sinusoidal wave by changing k, right? K is kind of the frequency. You can think of this frequency. You may, and then multiply again, you would generate a wave function that looks like this. So what I'm trying to tell you is that the wave function, the density of the electron locating at different on your linear chain could be different, and this k control how it look like, you know. So when k is not non-zero for one of the finite k value, it look like this. If you change the k, you change the sort of periodicity of the wave function like this. And so it really depends on this k value here. You change how your periodicity go and multiply your standard function like that. Okay, so this is the different function that look like physically look like, right? When you change k, you would expect they look different, and this is how they look different from the Brock perspective. Okay, so if you from this Brock function, we can of course these are real different wave function, right? Because they are different populated over the entire material that you have. and they are different. So you use this wave function to calculate energy, this wave function to calculate energy. You will generate